Check it out now, y'all.
NanoHub U, online instruction.
Okay, welcome back. We're going to talk in this lecture about quantum operators and expectation values, and we're going to try to explain how in quantum mechanics average values or expected values of different parameters are measured. So this is going to build on the discussion that we had about probability densities in the previous lecture. In terms of a quick review, just to remind you what we've established in prior lectures, we've said that you can write down the energy for a particle, right? And that energy is comprised of two terms. It's got a kinetic energy term K and a potential energy term U. And the potential energy term U is associated with how the particle interacts with its environment. The kinetic energy term K describes the energy associated with motion of the particle as it moves. There was this radical hypothesis that particles behaved as waves, and the question then became, well, how do these waves move in time and in space? And the idea was that if you would represent a particle wave or a matter wave by a wave function psi, which is represented by this complex function e to the I kx minus omega t, and if you could identify certain operators with the energies k and u, then you could write down an equation which is known as Schrödinger's equation, right, in one dimension. So in this identification, the kinetic energy K is defined or is identified with an operator that involves the second derivative with respect to position. The total energy E of the particle is then defined with the derivative of this wave function psi with respect to time. And what Schrödinger was able to show was that this differential equation is roughly equivalent to this simple statement that the kinetic energy plus the potential energy of this matter wave psi is equal to the total energy E times the matter wave psi back again, right? So the operation of this term in brackets, this term in bracket is going to be referred to as an operator. This operator operating on the wave function psi just gives you the total energy E times the wave function back again. So that's something that we discussed in the previous week's lectures. And I'll say that sometimes in shorthand, when you're discussing quantum mechanics in a shorthand way, this differential equation is approximated by a much simpler form, which just says H psi equals E psi, where H is assumed to represent everything in this bracket, and H is then referred to as the Hamiltonian operator. So very often in quantum mechanics, when you're dealing with the problem, what you have to do is you have to properly identify the Hamiltonian for that problem. And if you operate, if you let that Hamiltonian operator operate on the wave function psi, then you get the energy of the particle back out as an eigenvalue times the wave function psi again. So this is sort of the fundamental features of quantum mechanics that we established in week 2 of the course. And we did some simple examples to illustrate this general flow. What we'd like to do today is we'd like to generalize this concept in an important way. What we'd like to say is that in quantum mechanics, any observable, and in this case, the observable is going to be designated by small q, right? Any observable is just going to be assigned some sort of an operator, capital Q with a hat over it. And if we know what the operator is for a particular observable, if that operator operates on the wave function, then we like to believe that we're going to get an eigenvalue problem out, and the eigenvalue of that problem is going to be the observable q, small q, right? So This is sort of the fundamental structure of quantum mechanics, and it comes back over and over again. If you don't understand it now, you're going to have trouble throughout the rest of the course, because the whole course is built on this premise of operators and observables. And the operators operate on wave functions, and when those operators operate on wave functions, they give the observable that you would measure if you did hundreds of experiments, for instance. You'd give you the average value or the expectation value of the parameter that's of interest. And that parameter is just referred to as small q in this lecture. So, quantum mechanics can be taught as a sequence of postulates. You hypothesize or postulate certain things are true, and then you just sequentially follow the logic behind those postulates, and at the end of the day, you magically get an answer, right? I don't particularly like that approach because it does not build intuition, but it's worthwhile to at least on one slide try to represent the formalism of quantum mechanics, both in words and in math, and that's what I attempt to do in this slide. There are 6 basic statements that apply to virtually any quantum mechanical problem. I won't read through the words. This is more of a summary slide where you're going to have to study it on your own. But I will make the point that some of these things we've already introduced. So, for instance, we've introduced the concept of the wave function psi. We've introduced the concept of an eigenvalue problem where an operator times the wave function is equal to an eigenvalue times the wave function back again, right? We've introduced that. We've also introduced the time-dependent Schrödinger equation that tells how this wave function psi changes with time. In this lecture, we're going to focus mostly on this statement here, which says that the expectation value, or the average value of a quantity, is simply given by taking the operator associated with this quantity, putting it into the probability density psi star psi, and then integrating over the appropriate region in space. So if our wave function describes a 3-dimensional particle, we'd be integrating over 3 dimensions, so we'd have a volume integral that we would have to perform. And this mathematical structure is used all the time in quantum mechanics to obtain expectation values, which are basically the things that we measure in the lab when we measure small quantum systems. So the rest of the lecture is basically devoted to trying to understand this statement number 5. So up front, I want to try to distinguish 2 important cases, or 2 important situations, right? The majority of the course that we're taking this semester is focused on the first statement, or the first situation. And this first situation says that if I have a wave function which is an eigenvalue which is an eigenfunction of a particular quantum system, then if I operate on that eigenfunction by an operator q, I get an eigenvalue q sub I, which is characteristic of the eigenfunction psi sub I that goes into this equation, right? And so q sub I is referred to as the eigenvalue of the quantum state psi sub I, and repeated measurements of that quantum system would give this value q sub I. It's like the particle is in a well-defined state, and that well-defined state is represented by this wave function psi sub I, so that every time we make a measurement of this observable small q sub I, right, we get the same answer, we get the same value. So this would be the case, for instance, if psi sub I is an energy eigenvalue. If psi sub I is an energy eigenvalue, then capital Q is represented by the Hamiltonian H, and then the eigenvalue Q sub I is just the total energy E of the system. And every time we measure the total energy E of the system, we'd expect to get the same value because the system is basically confined to this one quantum state designated by psi sub I. I'll just say that doesn't have to be the case. Quantum mechanics is a lot more general, and it allows for the possibility that a particle could be in a mixed state described by a sum of wave functions. Each wave function psi sub I is known, and there are coefficients in front of each wave function that describe basically the probability that the electron is in a particular state I, right? And this is referred to as this quantum state capital psi is then referred to as being in a superposition of possible states psi sub I. And when you have a situation like this, then the measurement, the outcome of a measurement is not at all clear, right? If you make a measurement, it just depends on when the measurement is made and whether the state is in which state psi sub I at the time the measurement is made. So it's a much more dynamic and interesting situation than the situation where you know the particle is in a particular wave function psi sub I. The way you calculate the value or the result of a measurement when your quantum particle is in a mixed state, right? You then define this expectation value, which is often designated by these angular brackets, and you're basically then taking this operator capital Q, you're multiplying that operator by the probability density psi, and if the problem is a one-dimensional problem, then you're integrating over X, okay? So we're not going to really dwell on this part of quantum mechanics in this introductory course, but it's important for you to realize that this provides a considerable amount of flexibility in describing quantum systems. Most of the calculations we're going to do are going to be related to this much simpler statement of eigenvalues and eigenfunctions. In quantum mechanics, this probability density that we use is defined as psi star psi, and so we can say without loss of generality that the expectation value of a quantity, say small q, is given by a statement which should look very familiar to you if you listen to the last lecture on probability distributions and probability densities, right? So the expectation value of this observable q is given by taking the operator associated with this variable, putting it into the probability density psi star psi, integrating over all regions of X if we're focused on a one-dimensional problem. And we've got to divide by we have to have a normalizing factor in the denominator. This normalizing factor in the denominator is often set equal to unity if these wave functions are properly normalized, right? So this expectation value for Q with a properly normalized wave function then just simplifies to this statement, and this is referred to as the expectation value of a particular quantity. Okay, so this definition shouldn't be too terribly surprising because I can, if my wave functions are normalized, I can write the expectation value in this fashion without the denominator. The denominator is equal to unity, right? And this operator Q, operating on the wave function psi sub I, right, satisfies an eigenvalue problem, and it just gives back the eigen value Q sub 1 or Q sub I times the wave function back again. So I can substitute this equation into this equation, and I get this value, right? This quantity, the eigenvalue, is not dependent on position x, so it can come out of the integral, and I'm then left with a simple integral of this wave function over all space, and if the wave function is normalized, this integral is equal to unity, and it just says that the expectation value of this operator is just the eigenvalue q sub I. So in the case when a particle is confined to a particular wave function, and that particular wave function is designated by this notation psi sub I, the I is telling you the quantum number of that quantum state, right? So I could be the integers n that, for instance, we discussed for the one-dimensional infinite well problem last week, right? The subscript I is basically telling you that quantum number. So you've got to understand this notation, right? You've got to be able to use it. More importantly, you have to be able to set these integrals up and plug in the appropriate values and then actually evaluate the integral. So it's not only enough to evaluate the integral, but you've got to understand the formalism and the framework and build up to a resolution of a particular problem. I will say that some expectation values are incredibly easy to calculate. So for instance, you can imagine asking what the expectation value of a particle is along the x-axis. So let's, for the time being, let's just focus on one-dimensional quantum problem, right? And if we want to calculate the expectation value of position, we then would have to evaluate this integral. We'd have to divide by this factor here, right? But if the wave function is properly normalized, then we just have one integral to evaluate. We have to take the wave function and its complex conjugate, multiply it by x, and integrate over the range of x that's appropriate for the problem. If you, for instance, want to find the expectation value for the square of a particle's position x, right? Well, you have to represent that in terms of the symbol x squared with the angular brackets that refers to an expectation value. You would then put x squared into this standard definition, right? Again, it would simplify if your wave function is normalized to unity. And this quantity psi star psi that keeps appearing, right, is this probability density that we discussed in the previous lecture. So, as an example, let's say we want to calculate the expectation value for the position x and the position squared of an electron in, let's say, the n equals 2 quantum state of an infinite square well. So why would you want to do this? Well, in principle, you'd want to do it because either you have a measurement that allows you to measure x, or it allows you to measure x squared of an electron in an infinite square well. And let's say you want to compare those measurements to theoretical expectations. So what we're going to do is we're going to do the theoretical calculation here, and then, we're assuming there's some experiment that's been performed. You're going to compare that experiment to the theory. So the statement of the problem says the n equals 2 quantum state. So we have to go to our lookup table for eigenfunctions of the infinite square well. We have to select out the n equals 2 eigenvalue, right? The energy eigenvalue is of course, we've already derived that in the prior lecture. What we have to do here to get this value in terms of joules is we have to insert the mass of the electron in this expression for the energy eigenvalue. But for now, we're interested in the wave functions. The wave functions have been properly normalized, so that means that our calculation of expectation values are going to be simple. You also have to remember that because we're treating the particle as a wave, right, the actual position of the particle is not well defined, right? The wave has some extent to it, and the particle is delocalized over the extent that the wave is delocalized. So that means that you know, for a particle in a box, you could define, let's say, the expectation value of position, or the expectation value of the position squared. You could define that rigorously because you could localize the particle and you could tell where it is. The price you have to pay when you treat the particle as a wave is you have to do these calculations because in principle you don't know where the particle is located. What is x with the angle brackets around it? That refers to the expectation value of x when this particle is in the n equals 2 quantum state. Well, you just have to perform the calculation as we've outlined, right? You have to know what the wave function is, and then you have to put that wave function in an expression for the expectation value, and it involves psi star psi. So in this case, the wave function is real, so the complex conjugate of psi is just the same as psi, right? That allows you to get a sine squared term in the integral. X is the parameter that you're trying to calculate the expectation value of. Note that you have to change the limits of the integral because this is a finite square well. The width of the well goes from minus L/2 to plus L/2, so that has to be reflected in the mathematics for this expectation value calculation. You can simplify the calculation by recognizing that the first term is odd in x. That means as x goes from positive to negative, the polarity of x changes sign. On the other hand, sine squared is an even function. It does not change sign as x goes from positive to negative because it involves the sine squared. And anytime you've got an even function times an odd function integrated over symmetric limits, the integral by definition is going to be 0. So what this allows you to realize is that the average value of the x position, which is the number that you would obtain if you measured this particle in this quantum well many, many times, the average value is equal to 0. And the question is, what does that mean? And it just simply means that on average, the particle is on the right side of the well as many times as it's on the left side of the well. And if you make many, many measurements, on average, the average position of the particle would be 0. Right? So that's the implication of this calculation. The second question is, what is the expectation value for x squared? The calculation now is a little bit more detailed, but basically you're evaluating the integral of x squared times sine squared, where the wave function sine is the n equals 2 eigenfunction for the infinite square well. Now you can see what we have is we've got an even function x squared multiplied by an even function sine squared. So this integral is going to be non-zero. And I just work out the integral here. This identity is particularly useful. What you find is, after you evaluate the integral between the limits of minus L/2 and plus L/2, what you find out is that the average value of x squared is not 0. It's slightly shifted. It's 0.0708 times the width of the well squared. And it just simply means that, for instance, if you took the square of this x squared, you would basically get an RMS value for the particle's position. That RMS value turns out to be plus minus 0.266 times the distance times the width of the well L. So if you sit down and think about it, what you're basically doing is you're evaluating the integral of sine squared, but you're weighting it by this factor x squared. And so if you just plot x squared sine squared, you get this purple colored line, right? And it basically is showing you that the major contribution for that integral of x squared sine squared comes from values that are out near plus minus L by 4, which is pretty close to the plus minus 0.266 value of L that we obtained from the detailed calculation. So if you want to know how I go from here to here, I work out all the details on the next slide. That's something that you can go through on your own if you want to see how the calculation proceeds. To end the lecture, I just wanted to briefly discuss the superposition of quantum states that we discussed earlier in this lecture, and I want to set the problem up so that you have some appreciation for the power that quantum mechanics allows you when you think about particles that are not in eigenfunction states of a particular potential. So for here, let's suppose that we take a particle and we put it in an infinite well, and we somehow control the wave function of that particle, and we give that wave function a value that's designated by this capital psi that's indicated in red. And just to be specific, let's say that this wave function that we somehow prepare the particle in is characterized by a linear wave function, a triangular ramp that goes up and then back down to 0, right? So at x equals 0 and x equals L, the wave function is equal to 0, so it satisfies boundary conditions. But the shape of the wave function is clearly not one of the eigenvalues, or not one of the eigenfunctions that we solved for when we considered the infinite square well potential. What this equation is telling you is that you can decompose that wave function psi, which is not an eigenfunction for the infinite square well. You can decompose that into a sum of the eigenfunctions for the square well. And the decomposition involves these coefficients c sub I, and these coefficients c sub I are basically telling you how much psi 1, psi 2, psi 3, and so on is in this particular quantum state which you somehow prepared. So just by looking at this wave function and comparing it to the known shapes of the eigenfunctions for the infinite square well, you might guess that the coefficient C1 for the eigenstate psi 1 is a number close to unity, right? That because the shape of this wave function here is the closest match to this wave function here, right? Probably the wave function psi 2 is not going to contribute to this wave function because this is asymmetric about the center. This is not. So psi 3 is going to contribute some amount to this wave function. And what it just simply means is that if you measure, let's say, the energy of the particle when it's in this quantum state, right, the energy that you're going to measure is going to depend on what eigenstate you grab the particle in and when you make its measurement. So you're going to get a range of values for energies, and the statistical numbers that you measure are probably going to be dominated by this first quantum state. So this is a really important concept to understand. It's one of the underlying principles of quantum mechanics, and I hope this simple discussion gives you some insight. The scope of this course will not allow us to discuss this idea in too much more detail, but it's important for you to understand it. Finally, up next, the next lecture, we're going to talk about the momentum operator. So we're going to try to invent an operator which, when it operates on a wave function, gives the momentum of the particle that's in that wave function state. So that'll be the next topic. Thank you much.